In today's session, we get to talk about Archimedes' principle. Now, for us to understand Archimedes' principle, we need to first get well versed with what we mean by upthrust. So allow me to first explain what upthrust is and where it comes from. Now, first of all, when an object is put in water, like the one you're seeing, it experiences forces in all directions in this liquid. It will experience forces in that direction. It will experience forces in that direction. It will experience forces acting down on top of it and experience forces down on it. Of course, we all know that it's a property of pressure in liquids that pressure acts in all directions. So if you look at this solid, forces are acting on this solid from all directions. However, when you look at the forces on the sides, the forces on the sideways will always cancel out because they are more the same. So they will cancel out. But the forces acting downwards from down here are greater than the forces that are acting upwards. And as a result, the resultant in this case is such that we always have an upward force acting upwards. That upward force that acts upwards on this solid as it's in water is what we are calling the upthrust force. It's like when you drop in water and you are a swimmer, you always feel a certain kind of resistance acting on you in the upward direction as you're trying to move in water. That is for people who know how to swim, or if you've ever played around in a lake. When you immerse yourself fully in water, you always feel a certain resistance as you advance towards down. That resistance is the upward force acting on you, and that's what we are calling the upthrust force. Now that we have understood what upthrust actually means, now let's go on and describe the Archimedes principle. Now, the Archimedes principle simply put that when a body such as this one is partially or fully or wholly immersed in a fluid such as this, it is going to experience an upthrust force, and this upthrust force it is experiencing is supposed to be equivalent, or it is equal to the weight of the fluid that has been displaced by that solid. It's as simple as that. So this upthrust force, which is also known as the buoyancy, is simply the tendency of the liquid to exert an upward force on a body that is immersed inside it. As simple as that. So let's go ahead and do an example where we are required to use this Archimedes principle. A string supports a solid iron object of mass 0.18 kilograms totally immersed in a liquid of density 800 kilograms per meter cubed. Calculate the tension in the string if the density of the iron is 8,000 kilograms per meter cubed. First of all, we need to summarize the question. We'll do it diagrammatically. The question says that a string supports a solid iron object of mass 0.18 kilograms. So we are having a string right there. It is supporting this thing right there. And this thing, the weight of this thing is 0.18 kilograms. So meaning that this solid object, this iron object, the weight of this iron when it is in air is 0.18 kilograms. That is the weight of this thing. Now, the question says that the string supports a solid iron object of mass that totally immersed in a liquid. So this thing is totally immersed in a certain liquid. This is the iron. It's totally immersed in a liquid whose density, so the density of that liquid is 800 kilograms per meter cubed. They're asking us to calculate the tension in the string. Calculate the tension in the string if the density of iron is that. So the density of the iron, let's call it the density of that solid, is 8,000 kilograms per meter cubed. Yeah. So the density of that solid iron is 8,000. And they want us to find the tension in the string. Now, for us to find the tension in the string, I think there are two ways for us to do this. To begin with, the weight of this solid, let's say if this was, we had a spring balance here. This thing, at first probably it weighed 0.18 kilograms when it was dangling in air. If it is dangling in air and that is its weight in air, oh, by the way, this is not weight, this is mass. This is the mass in air. So it means that if we want to find the weight of this thing in air, its weight in air is going to be equal to its mass, 0.18 kilograms. Multiply that by the acceleration due to gravity, which is going to be 9.81. So it means that the weight of that solid when it is in air, it is going to be equal to 1.7658 newtons. So that is its weight in air. So now again, if it was dangling in air, it would mean that it would weigh 1.7658 newtons. Now this 1.7658 newtons would be the tension this string will be experiencing. Because let's face it, if this thing was in air like that alone, this is the weight of this thing as it's acting downwards. It means that the string is experiencing an equal but opposite force. So if this thing weighs 1.7658 newtons when it is in air, it means that if this body was dangling in air, it would be the tension experienced in the string would be exactly 1.7658 newtons. Now the scenario we are having here is that this thing right there is immersed in a liquid. If it is immersed in a liquid, the string is still experiencing a certain tension. So if it is immersed in a liquid, it means that the weight this thing is experiencing while it's in water is the same as the tension experienced by this. So meaning that the weight of this in water is equivalent to the tension experienced by the tension experienced by the string. So it means that it is as simple as that. That for us to be able to find the tension in the string, we simply have to find the weight of this iron in water. But well, I think we shall use that approach as an alternative. Right now, this video is about how we can use Archimedes principle to find this, to calculate this. So I'm going to first use Archimedes principle to find out the tension in this string. Then we can use this other alternative that I have just been explaining. So let's get started. First of all, this string, as it is here, this object, when it is in water, there are some forces that it is experiencing. If I may redraw that here, this is the iron solid. It is on this. This thing is immersed in water. And when it is immersed in water, it is experiencing tension. This tension is acting in the opposite direction. But while this thing is in water, this solid, it is experiencing some forces downwards. We have the weight of this thing acting downwards. The weight of the solid. Then upward we have the tension acting in that direction. And also because this thing is immersed in water, there is the upthrust force acting on this body. So for this to balance up the forces, we would say that first of all, the tension that is the upward forces are equal to the downward forces. So meaning that the tension experienced by the string upwards plus the upthrust is supposed to be equal to the total weight of this body acting downwards. Weight of the solid acting downwards. So now, what are we interested in? We are interested in the tension. So when we make tension the subject of the formula, it means that tension here, the tension experienced in the string is given by the weight of the solid when it is in air minus the upthrust. So our task is to find this and that, and then we will have the tension. So now, what is the weight of the solid in air? Of course, the weight of the solid in air is already given. We already found it here. The weight of the solid in air is 1.765 newtons. So it means that one we have it. We have the weight of the solid in air. So now our role here is to find the upthrust here. So now for us to go ahead and find the upthrust, we will derive the way we get upthrust from Archimedes principle. When we were beginning this session, we said that Archimedes' principle simply states that when a body is partially or wholly immersed in a fluid, it's going to experience an upthrust, and this upthrust is equivalent to the weight of the fluid that is displaced. So for us to be able to get this upthrust force right there, it is as good as getting the weight of the fluid displaced. So the question is that what is the weight of the fluid displaced? If we know the weight of the fluid that has been displaced, then we have the upthrust. So let's concentrate on first getting the upthrust first. So upthrust is going to be equal to weight of fluid displaced. Now we know that weight is given by mass times gravity. Now we already know the gravity, we need the mass. Now we do not know the mass of this fluid. It's not given in the question. But we know that mass is also given by density times volume. So for us to get the mass of the fluid, we need to get the density of the fluid, or let's call it the density of the liquid. Multiply that by the volume of the liquid. Volume of the liquid, multiply that by the gravity. So what does that give us? Now the density of the liquid is given, it is 800 kilograms, the density of this liquid. So the density in this case here is 800, multiply that by volume of the liquid displaced. If you realize the volume of the liquid displaced is the same as the volume of the solid that is displacing. So it means for us to get the volume of the liquid that was displaced, it is as good as getting the volume of that very solid, because this very solid, it can only displace its own volume of water. So it means that it's going to be the volume of the liquid displaced is the same as the volume of this solid. So the volume of the solid, since we do not have it directly, we can get it from the mass of the solid divided by that by the density of the solid, and multiply that by gravity, which is 9.81. So this is going to become 800, multiply that by, this is the volume of the liquid, this is volume of the liquid that is displaced is the same as the volume of the solid itself, which is given by the mass of the solid. The mass of the solid in this case is given in the question as 0.18 kilograms. The mass of the solid in air is 0.18 kilograms. 0.18 kilograms, divide that by the density of the solid, which is also given in the question as 8,000 kilograms per meters cubed. Multiply that by the gravity, which is 9.81, and that gives us an answer of 0.17658 newtons. So that's the upthrust force. Now that we have the upthrust force, we shall now go back and find the tension in the string. So it means that the tension is given by the weight of the solid minus upthrust. In this case, the weight is already given in the question. We already got it as 1.7658. Of course, this figure is gotten from here. This is the weight we got earlier, 1.7658. Subtract from the upthrust, which we've just gotten here as 0.17658. And when we subtract those two, we shall end up with 1.58922 newtons. And that is the tension experienced in the string. Now the alternative way of doing this is this. First of all, this string supports a solid iron object whose mass is 0.18 kilograms. So the mass of this solid iron, let me call it M subscript I, is 0.18 kilograms, and definitely this makes its weight, the weight of the solid iron is now 0.18 kilograms. Multiply that by the acceleration due to gravity, which is 9.81, and that gives us the weight of the solid iron as 1.765 newtons. And this is the weight of the solid iron when it is in air. So now, of course, it is totally immersed in a liquid of that density. So the density of the liquid we are talking about here is 800 kilograms per meter, and we are required to calculate the tension in the string. If the density of the ion in this case is 8,000 kilograms per meter cubed. Representing this diagrammatically shows this is the solid ion. Now, representing this diagrammatically means that this solid ion is immersed in a certain fluid. And if it is immersed in a certain fluid, it means that this string with which it is immersed within the fluid is experiencing a certain tension. So in other words, if they want us to find the tension that is experienced in the string, it's another way of asking us to find the weight of this solid ion when it is immersed in the fluid, because the weight of this solid ion when it's immersed in the fluid is equivalent to the tension that is being experienced in this string. So it is as simple as getting the weight of that solid ion. So to get started with with the calculations for the weight of the solid ion when it is immersed in this liquid, we shall begin by saying that relative density of a liquid is going to be equal to the apparent loss in weight of this solid ion when it is placed in this liquid, so which is going to be the weight of this solid ion when it is in air minus the weight when it is in the liquid, divide that by the weight when this solid ion is in air minus its weight when it is in water. So what we want here is this. We want to find the weight of this solid ion when it is in the liquid, and this weight is equivalent to the tension that is experienced by this string when it is in the liquid. So we need to find the rest of these parameters. So to find the rest of these parameters, we shall begin off first with the weight of this solid ion in air. The weight of the solid ion in air, we got it here as 1.7658 newtons. So it means that we already have that weight in air. So let's go ahead and find the relative density of the liquid. Now, from our question, to find the relative density of the liquid, we know that the primary definition of relative density, we know that relative density is given by the density of a substance, divide that by the density of water. And in this case, the density of the substance here, we are looking at this fluid or the liquid. The density of the liquid is 800, so it means it's going to be 800 kilograms per meter cubed. Divide that by the density of water, which is 1,000. And this is going to give us 0.8. That is the relative density. So meaning we found the relative density of the liquid. The relative density of the liquid is 0.8. So that is done. Now we need to find this, the weight of the air minus the weight of the water, or call it the apparent loss in weight of the solid when it is immersed in the water. Now, of course, we have the weight of the solid in air that has been given. We already have it. We already calculated it. But we do not have the weight of the solid in water. It's not given anywhere in the question. But if you think harder about this expression, the apparent loss in weight of the solid it can also be found in another equation. The relative density in liquids is given by the apparent loss in weight of a substance in the liquid, divide that by the apparent loss in weight of a substance when it is immersed in water. Likewise, when you're trying to find the relative density in solids, it's given by the weight of a substance when it is in air, divide that by the apparent weight in loss, the apparent loss in weight of that substance when it is immersed in water. Now you realize that this expression in the denominator is the same as that expression in the denominator. Now, getting back to our question, you see that in our question, one of the parameters that we need is that we need to find this expression, the apparent loss in weight of the substance when it is immersed in water. And if you look at our expression for relative density in a solid, you realize that it is the same expression in the denominator. In this question, we are dealing with the relative density of an ion that is immersed in water. So it means that if we attempt to find the relative density of that ion while using this expression, we will be able to find the expression here, which is exactly what we are looking for here. So we shall go ahead and attempt to find the relative density of the solid. So to find the relative density of the solid, we shall say relative density of the solid ion, let me call it that, is going to be equal to the weight of the solid ion in air, divide that by the apparent loss, which so happens to be the weight of the solid in air minus the weight of that same solid, ion solid in water. If I may write this here, this is the same as saying relative density. Now you realize that the relative density of the solid ion when it is in air is given by the density of the ion. So it's going to be density of the ion, divide that by the density of water, is still going to give us the weight of that ion in air, divide that by WA minus W subscript W. So the density of this ion when it is in, the density of this ion according to the question is 8,000, divide that by 1,000. This is the density of water, so this is the relative density of the ion, is given by its weight in air. Now we already know its weight in air, it was given to, we found it out earlier. Its weight in air is 1.7658 newtons. So this is going to become 1.7658 newtons, divide that by WA minus WW. So we shall end up with, when we make this the subject of the formula, WA minus WW, which we are most interested in, the expression, is giving us 0.220725 newtons. So looking back at where we've come from, we already have the relative density of the liquid. We got it as 0.8. We have got this expression, which is this right here. We have the weight of the solid ion in air, so we can go ahead and make WL the subject of the formula, and we're able to get the tension in the string. So to proceed with that, we shall do, if I may write this down, so the relative density of the liquid, we got that already as 0.8, so this is going to become 0.8 is equal to the weight in air, which we already got, the weight of the solid ion in air, which we got as 1.7658 newtons, minus the weight of the solid in the liquid, which we are looking for, which is equivalent to the tension, divide that by this expression, which we already got as 0.220725 newtons. So when we make WL the subject of the formula, we shall end up with 1.58922 newtons. And so this happens to be the tension that is being experienced by that spring. In today's session, we are going to explore the proof of Archimedes' principle. Now, like we have been discussing earlier, Archimedes' principle simply states that when a body is wholly or partially immersed in a fluid, it is going to experience an upthrust, and that upthrust is equivalent to the weight of the fluid that has been displaced. Now, when we say that in this session we are going to prove Archimedes' principle, we are actually trying to prove that theory, or we are trying to prove Archimedes' principle, that actually when this solid you're seeing right there is inside this liquid, the upthrust it is going to experience is equivalent to the weight of the fluid this solid has displaced. That is what we are going to prove. In beginning to prove this, one, we need to know that this is a solid right here that has been put in a container full of a liquid. Let's call this a liquid of density rho. One of the properties of pressure in fluids is that pressure in fluids acts in all directions. So when we put a solid such as this one in a fluid like this, in this case probably this liquid right here, this solid is going to experience pressure in all directions. There's going to be pressure acting in that direction, in that direction, then you're going to have pressure downward and then the pressure on top. Now of course the pressure in this direction and the pressure from that direction, this pressure are the same, so they cancel out. But if you look at the fluid pressure down here, the liquid pressure experienced from down below on face DC, that fluid pressure is greater than the fluid pressure experienced by that on top up. And as a result, it means that there's going to be a resultant force acting on this solid in the upward direction. Now that resultant force that is acting on this solid in the upward direction is what we are calling upthrust. So what is upthrust? Like we had earlier said, upthrust is simply defined as that upward force that is experienced by all objects that are totally or partially immersed in a fluid. And by fluid, I mean a liquid or a gas. So this upthrust force that is acting on that on this solid, that resultant upthrust force, according to Archimedes, he says that the magnitude of that force is equivalent to the weight of the fluid that has been displaced by this solid. So we are going to go ahead and prove that. And we are going to prove that by first of all finding the magnitude of that upthrust force. So this is our diagram, and now we are going to first find the pressure on side AB. This is the top part. The pressure acting on top of that, right there. The pressure on side AB is given by the atmospheric pressure, which we've denoted as H, plus, now of course the pressure acting on that level, this is the height H1 of the liquid, which is the height H1 of the liquid times the density of the liquid, which is right there, times the acceleration due to gravity. So that is the pressure on this side. Then of course, as a result, since we have the pressure now, we can go ahead and find the force, the downward force acting on side AB. The downward force acting on side AB is going to be the pressure exerted, which is this one, times A. Of course, all this is coming from this. We all know that pressure is the force acting normally per unit area. So it means that if we want to find the force, of course force is simply going to be pressure times area. This is where this is coming from, that the downward force acting on AB is given by the pressure, the liquid pressure, which is comprised of the atmospheric pressure plus the fluid pressure due to the depth H1 times the area, like that. So that is for AB. Then we are going to do so for AB, then we are going to do so for DC as well. So the fluid pressure acting downwards on DC is given by still the atmospheric pressure, the pressure acting on that level. Remember, pressure in liquids increases with depth, or it depends on depth. So the height from the surface up to that, the level on DC where DC is at, the pressure acting on that level is given by H plus the height H2 times the density of the liquid times gravity, and of course the upward force acting there is going to still be the pressure given times the area, the cross-sectional area of that solid or on that face DC. And we said that the forces acting on this way and that way, on face AD and BC, they cancel out because they are the same. So we shall not go into them, we shall go into these ones. We know that this one right here is greater than this one, so it means that upthrust force is going to be equal to the resultant upward force. Now of course the resultant upward force, we have this is the one acting on DC is this one, which is pressure times area, minus the one acting on top, which is less, which is this one, atmospheric pressure times that. This is the whole thing, the pressure times the area. When we subtract those two, of course we open brackets. This is A times H giving us HA. Then we have the area times H2 giving us area times this whole term gives us H2 rho G times area, minus open brackets, area times H gives us HA. Then area times H1 rho G gives us H1 rho G times A. Then when we go ahead with our working, of course these HA's cancel out. This HA minus HA, this cancel out. You remain with H2 rho GA minus H1 rho GA, which is H1 rho GA, right there. So you find that we have an expression here where we have, of course, these terminologies are the same. We factor them out. That is the density of the liquid times the acceleration due to gravity times this cross-sectional area outside the brackets into h2 minus h1. And now this is our expression for upthrust, and we call that our equation 1. So after getting our expression for the upthrust, we need to determine is this expression going to be the same if we're trying to attempt to find the weight of the fluid that has been displaced? So this is our first part of our proof. We have gotten the expression for upthrust as this. So now let's go ahead and find the expression for the weight of the fluid that has been displaced by this solid. So the weight of the fluid that has been displaced is given by the mass of this fluid that has been displaced times the gravity. Of course, now the mass of the fluid mass is given by the density of the fluid times the volume of the fluid. This is density of the fluid times the volume of the fluid times gravity. Now, of course, the density of the fluid is right here. This is the density of the fluid. Multiply that by the volume of the fluid. Now, of course, we do not know the volume of the fluid, but we know that if the solid has a volume of, let's say, 10 centimeters cubed, it means this solid, the 10 centimeters cubed of the solid will displace 10 centimeters cubed of the fluid. What am I trying to say? What I'm trying to say is that a solid will only displace its own volume of fluid. So it means that the volume of this fluid is equivalent of the fluid that has been displaced is equivalent to the volume of the solid that has displaced that fluid. So we can as well compute it from the volume of the solid. So the volume of the fluid here is, we shall give it by the volume of the solid. Of course, the volume of the solid is going to be the cross-sectional area of this solid, which we have labeled as A, times the change in the height of the solid. Cross-sectional area times height, and of course the height here is given by h2 minus h1, which so happens to be this h2 minus this h1, so that we're able to get that height, the height of the solid, times gravity. And so we end up with our expression as density times gravity times area into h2 minus h1. Now this is our expression for the weight of fluid displaced. The first expression we got was density, was this. This is the upthrust. And then the other expression we are getting of the weight of the fluid displaced is looking like this. Now you realize that the expression for upthrust is the same as the expression for the weight of fluid displaced. And so from that kind, we come to the conclusion that it is indeed true, or it has been proven, that Archimedes' principle, which states that the upthrust experienced by a body that has been wholly or partially immersed in a fluid is equivalent to the weight of the fluid that has been displaced, is indeed true. Or in other words, it is therefore true that when a body is wholly or partially immersed in a fluid, the upthrust it experiences is equivalent to the weight of the fluid displaced. In this session, we are going to look at one of the applications of Archimedes' principle. We are going to describe some procedures on how to measure relative density of a liquid using a balanced lever. And this is how our procedure is going to be like. Of course, right there, what we have there is a balanced lever. That's a lever with a weight whose W, this is a known weight, we know this weight, W. Of course, D1 is going to be the distance from the known weight to the pivot. Then D is going to be a fixed distance that we are going to maintain throughout our experiment from our pivot to a weight whose W1, which weight we do not know. So to begin off, of course, we are going to use a known weight, and we are going to balance this known weight with this sinker that we have, whose weight is W1. We are going to balance them, and after balancing them, we shall get the distance D1 from the pivot to the known weight, and the distance D. After balancing them off, we measure and record D1 and D. And when we do so, we shall take moments about this pivot. Now, I assume by the time you're watching this video that you are well conversant, or you know what I mean by principle of moments. Of course, principle of moments is that clockwise moments are equal to anti-clockwise moments. So we are going to take moments about that pivot, and so it's going to be that W1 times the distance there is it going to be equal to W, multiply that by the distance D1. Now we're interested in finding the weight of this W1. So it means that we make W1 the subject of the formula. When we make that the subject of the formula, this is going to end up being W times D1 over D. We call that our expression 1. Our expression 1 is actually the weight of this sinker. And let's call this, the weight of the sinker is more like saying the weight of this sinker when it is in air. After that, we are going to immerse this sinker in water. So this sinker is now immersed in water, as we have seen right here. The sinker, after immersing it in water, we definitely, remember, we keep this D constant. And so what we do is that we are going to adjust the distance between the pivot and the known weight until this lever balances. And when it balances, we measure and record the distance D2 and definitely after measuring the distance D2, we go ahead and take moments about the pivot. Taking moments about the pivot in this case is going to give us the weight W2, multiply that by the distance, the constant distance D, is equal to the known weight W times the distance D2. So meaning our W2, our new weight when this sinker is in water is given by W, multiply that by D2, divide that by D. So that is our second expression, W2. So we are going to repeat this same thing, but instead we are going to dip this sinker into a liquid whose relative density we are looking for. And that is exactly what we've done here. We have kept this D still, it is still constant. We take away the water and so we dip this sinker into a liquid whose relative density we are looking for, and we adjust this weight, this known weight, and we get another distance from the pivot. We call it D3. And after doing that, we go ahead and find moments about the pivot. Clockwise moments, we take moments about that pivot, so it means that it's going to be W3 times the distance D. W3 times the distance D is going to be equal to the known weight W, multiply that by the distance D3. So W3 in this case is going to become W, multiply that by D3, divide that by D. And this is the third expression right there. Now if you already realize, you see that actually we are using this lever to try to get us the weight of this sinker in three different conditions. We first got the weight of that sinker when it was in air. Then again we got the weight of that sinker when it was in water. And again we got the weight of that sinker when it was in a liquid whose relative density we are looking for. So from our theory, we know that relative density of a liquid is, we are going to get the apparent loss of weight of the sinker in the liquid, divide that by the apparent loss of weight of that sinker in water. And so if I may use abbreviations here, the apparent loss of weight of the sinker, or of a solid over a substance in the liquid, in this case it's going to be the weight of the sinker, or the weight of the substance in air, minus the weight of the sinker when it is in the liquid, divide that by the weight of the sinker when it is in air minus the weight of the sinker when it is in water. This difference in weight is the same as saying the upthrust experienced by the sinker when it was in the liquid, divide that by the upthrust that was experienced by the sinker when it was in water. The weight of the sinker when it is in air is W1. It is what we got here when we put it on lever. When W1 was hanging just alone, this is the weight of this sinker when it is in air. So it means this is the same as saying this is going to be W1 minus the weight of the sinker when it was in the liquid. According to our experiment, when the thing was in the liquid whose relative density we want, that was W3. So that's going to be minus W3. Divide that by weight in air, which is W1, minus the weight when it is in water. And from our experiment, the weight when it was in water is W2. W2. So we will go ahead and make the necessary substitutions. What is W1? W1 is W times D. This is given by W times D1 minus, divide that by D, minus W3. W3 is given by W times D3, divide that by D, divide all that by W1 still, which is W times D1 over D, minus W2. What is W2? W2 is W dot D2, W multiply that by D2 over D. And of course this is going to become W dot D1 minus W dot D3. Divide that by the LCM here becomes D. Divide that by this, which is going to become W dot D1 minus W dot D2. Divide that by the LCM here is D. So this is going to end up being, W is common here, so we shall put W outside the brackets into D1 minus D3. Divide that by D. Divide that by W is common, so we put W outside the brackets here into D1 minus D2. Divide that by D. So this becomes W into D1 minus D3, divide that by D, multiply that by, with right here the reciprocal over W into D1 minus D2. And this is definitely going to end up with, this W cancels with that one, this D cancels with that. We end up with an expression as D1 minus D3, divide that by D1 minus D2. And with this expression, we are able to measure the relative density of a liquid using a balanced lever. In this session, we are going to show how to measure the relative density of a solid using a balanced lever. This is our procedure. Of course, before we get into the procedure, we are going to use this balanced lever right here. This is a lever that's a fulcrum. This is a weight W, whose weight we know. We call this a known weight. And this is W1, whose weight we do not know. So what we do is that first of all, we are going to balance this lever. We are going to balance this known weight with this unknown weight. And after this lever is balanced with these two weights there, we then go ahead and balance it off. We measure D1, the distance between the known weight and the fulcrum, and also the distance D, the distance between the fulcrum or the pivot and the unknown weight. Now the distance D is going to be maintained constantly throughout the entire experiment. But this D1 will be changed depending on whatever new measurements we'll be doing. So of course here it's going to be W. We're taking moments. W times that distance from the fulcrum, which is D1, is given by W1 times the distance D1 times the distance D. And from here we go ahead and find the weight that we do not know, W1, by making it the subject of the formula. And this is our first expression. Our first expression here, we're trying, this W1 is equivalent to, or it's representing the weight of this sinker in air. Drop this sinker in water, and when we get this sinker in water, we keep this distance D constant, and then we only adjust the distance D2, the distance between the fulcrum and the known weight. Then afterwards we take moments. W times D2 is going to be equal to W2 times the constant weight distance D. And then we go ahead and find W2, the weight of this sinker when it is dipped in water. Now from our theory, we know that when you're trying to find the relative density of a solid, it is given by the weight in air divide that by the apparent loss in weight of that solid. Now, of course, the weight in air is given by WA. That's the acronym we are giving it. Divide that by the apparent loss in weight. The apparent loss in weight of the solid is the weight in air minus the weight when that solid is in water. Now, according to our experiment, the weight in air in this case is given by W1. W1 is our weight in air. So in this case here, this is going to become W1. Divide that by the weight in air still, which is W1 minus the weight when it is dipped in water. When the sinker was dipped in water, we labeled that W2. So we go ahead and make the necessary substitutions. This W1 is this. W1 is the same as W times D1. Divide that by D. Divide that by, we are going to divide that by the apparent loss in weight of the solid. And of course, the apparent loss in weight is equivalent to the upthrust that body experiences when it is dipped in the water. So that is going to be divide that by W2. Of course, this is divided by W1, which is still W D1 over D. Subtract that minus W2, which is this, W D2 over D. To continue, this becomes W D1, divide that by D, divide that by, this is W D1 minus W D2, divide that by D. This becomes W D1 over D, multiply that by D, the reciprocal of this, which is W outside the brackets, into D1 minus D2. This D goes with that D, this W cancels with that W. You remain with an expression such as D1, divide that by D1 minus D2. And with that kind of expression, after using that experiment, you are able to measure the relative density of a solid using a balanced lever. We get to do some worked examples on Archimedes principle. This first one goes: a concrete block of mass 2.7 times 10 to the power 3 kilograms and the volume of that is totally immersed in seawater of this density. Find the weight of the block in air and Hydrometer the weight of the block in seawater. Now let's first remind ourselves that this should always be running at the back of our minds. That when we are dealing with Archimedes principle, the weight of the fluid that has been displaced is equivalent to the upthrust that has been experienced by that body that has been sunk in the fluid, either wholly or partially. So to begin off with Roman 1, weight of the block in air, of course this is more straightforward. We know that weight is given by mass times gravity. What is the mass of this concrete block we are talking about? The mass is 2.7 times 10 to the power 3. So it's 2.7 times 10 to the power 3 kilograms. Multiply that by the gravity. In all my videos, I'll be using gravity as 9.81. So this is going to give us 2.6487. Multiply that by 10 to the power 4 newtons. So that is the weight of the block in air. Unless otherwise stated, in all my videos, the value for G or the value for gravity will always be 9.81. So that's Roman 1 answered. So let's look at what the weight of block in seawater is like. So let's call this our seawater. We have this block in this seawater. Of course, now when this block is in seawater, it's experiencing what kind of force is it experiencing? It is experiencing an upthrust force. Let's call it that upthrust force. That is the force acting upwards. Then it also has the force acting downwards, and this force acting downwards is the force due to its weight. So of course, now that it is in seawater, it is having this force, its weight acting downwards. That is the weight when it is in air. acting downwards versus its upthrust, the upthrust force acting on it upwards. The difference between these two forces is going to give us the weight of this thing when it is in the fluid. In other words, what I'm trying to say is that when this thing, before this block was immersed in this fluid, it was at first dangling in air. When it was in air, its weight is what was acting downwards. Its weight in air. It was acting, its weight, it is just its weight in air that was acting downwards, and upwards there was no force. Then we get this block with its weight still acting downwards, then we come and dip it in water here. When we dip it in water here, it experiences now another upward force acting on it. So it means that this upward force, the upthrust force, is going to counteract some of this weight acting downwards. So when it counteracts some of it, it means that this block is going to lose some weight. That is what we call the apparent loss in weight of this solid. Now that apparent loss in weight of that solid means that this weight, when it was in air, has been reduced to a new weight. That new weight it has been reduced to is what we are calling the weight of this fluid when it is dipped in the seawater. So it means that for us to get the weight of the block in water, we are going to say weight in air minus the upthrust. So what is our weight in air? We already got our weight in air in our previous calculation. That was Roman 1. Our weight in air, we got it as 2.6487 times 10 to the power 4. So our weight in air is 2.6487 times 10 to the power 4. So that's going to be minus the upthrust. Now the issue here is that we do not know the upthrust. So it means we need to first go and first get the upthrust. After getting the upthrust, we come back and deal with this. Is the same as the weight, and we know that weight of the fluid displaced is given by mass times gravity. What is mass? The mass of this block, the mass of the fluid that has been displaced. Of course, we do not know the mass of the fluid that has been displaced, but mass is given by density. That is the density of the water, because we are dealing with seawater, right? So density of the water, multiply that by the volume of the water, and multiply that by the gravity. So of course this is going to become, now the density of the water, the question says that the density of the seawater is this. So it's 1.03 times 10 to the power 3. Multiply that by the volume of the water. Now the volume of the water is of the water that was displaced is equivalent to the volume of the concrete block that is displacing the water. And according to our question, the concrete block, they tell us, is of this mass, and the volume of that concrete block is 0.93 meters squared. So if the volume of the concrete block is 0.93 meters squared, it means that that's the same volume that was displaced, the volume of the water. So it's going to be times 0.9 times 10 to 0.9 meters cubed, multiply that by gravity, which is in this case 9.81, and so our answer there definitely is going to be 9093.87 newtons. This is our upthrust force. Now that we've gotten our upthrust force, we can go ahead and finish up with our earlier calculation. Our calculation required us to find the weight of the block in water, which is the weight in air minus the upthrust. In this case, this is going to become 2.6487 times 10 to the power 4 minus the upthrust force, which is right there, 9093.87 newtons. And definitely that's going to give us 1.74 times 10 to the power 4 newtons, and this definitely is the answer, and it is the weight of the block in water. And in some cases they might ask you to find the tension. If this block was tied on a string, what is the tension in the string when this block is immersed in water? The tension that is experienced in this string when this block is immersed in this water is the same as the weight of that block when it is actually in water, which so happens to be this. A string supports a solid of mass 5 kilograms, and this string is a string supports a solid of mass 5 kilograms totally immersed in a liquid of density 800 kilograms per meter cubed. Find the tension in the string if the object has a density of 2575 kilograms per meters cubed. This question is related to what we've been doing earlier. Let's summarize it, or I like drawing diagrams to get a clear picture of what I'm up against. So this is a string. This is a string. It is supporting a solid of mass 5 kilograms. So it means that the mass of this solid is 5 kilograms. And the density, it's in a liquid of density. So this thing is immersed in a liquid. And the density of the liquid is that. So the density of the liquid is 800 kilograms per meter cubed. Find the tension in the string. We need to find the tension in the string if the object has a density. So the density of this object, let's call it the density of the solid, is given by 2575. That is kilograms per meter cubed. Now again, this string is supporting this solid. This solid is already here in the liquid. So the tension that is experienced by this is equivalent to the weight of that block when it is in this liquid. So if we want to find the tension experienced by this string, we are simply going to find the weight of this block when it is in the liquid. So we get started with the working. Of course, we know, like we had done in our earlier question, that for us to be able to find the tension in this string, it is the same as the weight of this block when it is in the liquid. And getting the weight of that solid when it is in the liquid, it's the same as getting the weight of this block when it is in air, which minus the upthrust. So weight of that solid when it is in the liquid is going to be given by the weight of that solid when it is in air minus the upthrust force. And this is still going to be given by, now what is the weight of this thing when it is in air? We have mass. We have the mass of the solid. We do not have the weight. But we can still find the mass. We know, okay, we got to find the weight of this. The weight of this solid when it is in air is given by 5 kilograms, multiply that by the gravity, which is 9.81. So we come and put that here. So this is going to be 5 times 9.81. That's the weight of this solid in air, minus the upthrust. Now, of course, we do not know the upthrust, but we know that upthrust is equivalent to the weight of the fluid displaced. So we continue with our working. This is going to be 49.05 minus the upthrust. Now, upthrust is the same as weight. So this is going to become 49.05 minus the weight of the fluid displaced is the mass of that fluid. Let's call it the liquid instead. Mass of the liquid, multiply that by the gravity. This is going to be 49.05 minus the mass of the liquid is given by the density of the liquid, multiply that by the volume of the liquid, then multiply that by gravity. This is still going to give us 49.05 minus the density of the liquid is given by 800. That's the density of the liquid right here. It's 800 kilograms per meter cubed. Multiply that by the volume of the liquid. Of course, the volume of the liquid that has been displaced is the same as the volume of the solid itself. So if we get the volume of this solid, then we know the volume of the liquid that has been displaced. So now what's the volume of this solid? The volume of this solid, according to our question, has not been given to us directly, but we have some information that can help us get the volume of this solid. If we maybe do some volume is going to be equal to, we know that density is going to be mass over volume. So if we make V the subject of the formula, we know that volume is given by mass over density. So and according to this question, we do have the mass of this solid. The mass of the solid was given to us here as 5 kilograms. And we also do have the density of this solid, and the density of this solid was also given to us right there. So if we get the mass of the solid and divide by the density of the solid, we will be able to get the volume of the liquid, because the volume of the liquid that has been displaced is equivalent to the volume of the solid that displaces that liquid. So the volume of the liquid here, let me first write the initials here. It's going to be equal to the mass of the solid, divide that by the density of the solid, multiply that by gravity. So we continue with our calculation. So this is going to become 49.05 minus, this is giving us 800, multiply that by the mass of the solid. Of course, the mass of the solid is 5 kilograms, so it is into 5, divide that by the density. The density is 2575, so this is going to become 2575, multiply that by 9.81, like that. So definitely this, computing this whole thing, is going to give us 33.81 newtons. So 33.81 newtons becomes the tension. This becomes the tension in the string. There is an alternative way of doing this number that I would like to show. Remember one of our formulas from our previous workings? We know that relative density of a liquid is given by the upthrust experienced by a solid when it is in the liquid, divide that by the upthrust experienced by a solid when it is in water. And this upthrust, we are talking about the apparent loss in weight of that solid when it is in liquid, given by the apparent loss in weight when it is in water, the solid. So this is given by, of course, it's given by the weight of the solid when it is in air minus the weight of that solid when it is in the liquid. Divide that by the weight of that solid when it is in air minus the weight of that solid when it is in water. That is relative density of a liquid. Now, right here, now if you look at that formula, look, the question says, requires us to find the tension in the string. And the tension in the string is the same as the weight of that solid when it is in the liquid. In this case, our liquid here we are talking about is seawater. In this case, our liquid we are talking about is a liquid of density 800 kilograms per meter cubed. So now this is the liquid we are talking about. So the weight that is the weight of that of the solid mass when it is in the liquid is equivalent to the tension that is experienced in the string when that solid mass is in this liquid. So if we get this WL, the weight of the solid mass when it is in the liquid, that is equivalent to the tension. But now the question is that for us to be able to get this term, are we able to find the weight in air? Yes, we have the weight of the solid in air. We already have it actually here. The weight in air is 5 times 9.81. So we can get this term. We can get the relative density of the liquid. Remember, the relative density of a liquid is the ratio of the density of the liquid to density of water. We have the density of this liquid already. It's given us 800 kilograms per meter cubed. Divide that by the density of water, which is 1000. So we can get this figure. So we can also get this figure. Then there is this, the loss in weight in water. Now, of course, the weight in loss in the upthrust that is experienced in water, or the apparent loss in weight of the solid mass when it is immersed in water, we can still get this term by looking at the formula for relative density in a solid. Relative density in a solid is given by the density in can be given by the weight of the solid in air, divide that by the apparent loss in weight, which is this, when it is in water, and you can get this. So let's get started with the working to get this. Let's begin by getting the weight in air, which is obvious. Of course, our weight in air is given by the weight of the solid mass in air. The weight of the solid mass in air is given by 5 kilograms. Multiply that by 9.81, and definitely that we already got that as 49.05 newtons. So we have our weight in air. So let's go ahead and find the relative density of the liquid. We also know that relative density of the liquid, from the definition of relative density, it's going to be the density of the liquid divided that by the density of water. That is going to give us the density of the liquid, which according to our question, the density of the liquid is 800 kilograms per meter cubed. So it is 800, divide that by the density of water, which is a standard 1000. So this is going to be 0.8. So that's the relative density of the liquid. So looking at our formula here, we have the density, we have gotten that. Now we need to get this expression. The apparent loss in weight of the solid substance, or of the solid mass when it is immersed in water. So from still our formula for relative density of solids, we know that relative density of solids can be given we can get it in two ways. We can either get it by saying it's the density of the solid over the density of water, or we can still get it also by saying it is the mass, or the weight of the solid when it is air and in air, divide that by the weight of the solid, the apparent loss in weight of the solid when in water. Now the apparent loss in weight of the solid when it is in water is what is WA minus WW, WA minus WW. This is what we want. We want this expression, this one. So this is going to be given by, now of course the relative density of solid is, we have the density of the solid already in the question. Do we? Yes, the density has, the object has a density of 2575. So this is density of the solid is going to be 2575. Divide that by the density of water, which is 1000. This is going to be equal to its weight in air, which we got. Its weight in air, we got it as 49.05. So this is going to be 49.05. Divide that by this, WA minus WW, the apparent loss in weight when it is dipped in water. And this is what we want. When we make this the subject of the formula, this is going to become WA minus WW is going to become 49.05 times 1000. Divide that by 2575. So now that we've got the expression here, we go back to our original expression. Our original expression is right there. Let me write it here. Now we already got our relative density in the liquid as 0.8 right there. So right here we have 0.8 is going to be equal to our weight in air, the weight of the solid substance in air, which is 49.05 newtons, minus the weight of the solid substance when it's dipped in the liquid. Divide that by WA minus WW. We got the expression for that as, which is 49050 over 2575. So we work towards changing the subject of the formula, because when we make this WT the subject of the formula, this is the same as the tension. So when we multiply this on both sides, this becomes 0.8. The weight of the solid substance in the liquid is the same as the tension we are looking for. When you compute this, you're supposed to be getting 33.81 newtons. Before us is a very simple diagram. This is just a basin with some water, and right here we are looking at probably a log, something wooden. This wooden solid substance is floating on top of this water, as you can see. So now, as this is floating, we all know, or it should be common knowledge, that anything that floats on top of a liquid, it does so because it is less dense. For example, in this case, we are having this water and we are having this solid mass. This solid mass is able to float on water because its density is less than the density of water, or in other words, it's less dense than the density of this water. However, for the solids that, or substances that are able to sink in water, they are able to do so because their density is greater, or it's more than the density of water. So let's concentrate on the floating thing. For those substances whose density is less than the density of water, and as a result, they float. This thing, while it is floating, as you can see, it is digging itself into the surface of this liquid. In other words, what I'm trying to say is that a portion of this substance is embedded in the surface of the liquid, and part of it is exposed on top. Now, of course, this portion that is into the surface of the liquid, in doing so, it displaces some of this liquid. Some of this water is displaced as a result of this floating body. So what does that mean? It simply means that all bodies that float on water, there is a certain amount of liquid they displace, so that, in other words, some part of it is exposed up and some other part is displaced. Some other part of the solid displaces some liquid. And in today's video, we are concerned about that liquid that is displaced. That liquid that is displaced is definitely equivalent to the volume of that portion that has displaced it. But if you get that liquid that has been displaced and you probably weigh it, the weight of that liquid that has been displaced by a body that is floating is equivalent to the weight of the entire body that is floating. And that right there, ladies and gentlemen, is what we are calling the law of flotation. In other words, the law of flotation simply states that any floating body, or a floating body, will displace its own weight of fluid in which it is placed. So let's take note again that a body will only float in a liquid if its density is less than that of the fluid in which it is placed. We should also take note that the weight of a floating body is equal to the weight of the fluid it has displaced. That is what the law says. But the volume of the body that has been submerged, remember, as this thing is floating, it is just a portion of its volume that is submerged. So the volume of the body that has been submerged is equal to the volume of the fluid that has been displaced. And of course, the mass of the floating body is equal to the mass of the fluid that has been displaced. So we'll go ahead and do some examples that require us to use the law of flotation in our interpretation. Right here we have a cubical block of steel, 12 centimeters on each side, is floating on mercury in a vessel. The density of steel is 7,800 kilograms per meter cubed, and that of mercury is 13,600 kilograms per meter cubed. What is the height of the block above the mercury level? Let's summarize this question with a diagram so that we get a clear picture of what we are up against. 12 centimeters, meaning that every side is 12 centimeters. It's a cube. It is floating on the mercury in a vessel. So this thing is in a vessel, and the liquid it's floating on here is actually mercury. Now the density of steel is 7,800 kilograms per meter cubed, and that of mercury, of course, the density of mercury is 13600. What is the height of the block above the mercury. So let's say this is where the mercury cuts. All this is mercury. The question requires us to find the height of the block above the mercury level. Of course, for us to be able to find the height of the block above the mercury level, we need to know the height of the block that is embedded within the mercury level. But still, we shall use the law of flotation to help us interpret this. Like we had earlier stated, the law of flotation states that the weight of the block is going to displace an equivalent weight of the mercury. In other words, as this block is floating, its weight is going to be equivalent to the amount of mercury it's going to displace. So we shall begin from that point, that the weight of the block is equal to the weight of the mercury displaced. So of course the weight of the block is given, what we're looking for here is this height. So definitely the weight of the block here is given by the mass of the block, multiply that by the gravity, is given by the weight of the mercury displaced, which is going to be given by the mass of the mercury, multiply that by the gravity. Of course, we are having gravity here and gravity here. This g and that g can as well cancel out at that stage because it's 9.81, 9.81. So what is the mass of the block? The mass of the block is given by, we know from the formula, density is equal to mass over volume. So if you make mass the subject of the formula, mass is given by density times volume. So the mass of the block is given by the density of the block, multiply that by the volume of the block. This is still going to give us the mass of mercury, which is given by the density of the mercury. Let me call this M. The density of the mercury, multiply that by the volume of the mercury. Now the volume of the mercury we are talking about here is the volume of the mercury that has been displaced. So this is going to be given by, of course now we know the density of the block, we know the volume of the block. The block is such that it is having 12 everywhere. It's a cube, each side is 12 centimeters, so it means that we have the length, the width, and the height of the volume of the block. It is given. That is going to be equal to the density of the mercury, which is also given, 13600 kilograms per meter cubed. Multiply that by the volume of the mercury. Now the volume of the mercury is the volume of the mercury that has been displaced. The density of the block, multiply that by the volume of the block, is given by the density of the mercury, multiply that by the volume of the mercury that has been displaced. Now the volume of the mercury that has been displaced is equivalent to the volume of the block that has sunk in. Remember, this is a floating body. When it is floating, not the entire volume of this cuboid is going to float inside. Part of it will float, will sink into the mercury, part of it will remain out. So to find the volume of the mercury that has been displaced, the volume of the mercury that has been displaced is equivalent to the volume of this cuboid that has sunk into the mercury surface, that has displaced. So it means that to find the volume that has actually displaced or that has gone into the surface of this mercury level, it is as simple as getting the cross-sectional area of this cuboid, multiply that by the height that has sunk into the surface of mercury. So the volume of the mercury that has been displaced is equivalent to the cross-sectional area of this cube, multiply that by the height of the mercury, or the height of the block that has sunk in. So to get the height that has sunk in, let's call it H1. So you make H1 the subject of the formula. So this becomes H1 is going to be equal to the density of the block, multiply that by the volume of the block, divide that by the density of the mercury, multiply that by the cross-sectional area of that cuboid to get the height of the block that sank into the surface. So in this case, the density of the block is given in the question as 7.8. Of course, this is density of the block, or the density of the solid block, given by 7,800. Now this 7,800 is in kilograms. per meter cubed. Multiply that by the volume of the block. Of course, the volume of the block, it is 12 centimeters all through, so it is 12 times 12 times 12. Let me repeat this here in a bigger space. So this is going to become, the density of the block is 7. Divide that all by the density of the material, which is 13600. This is in kilograms per meter cubed. Multiply that by the area. Now the cross-sectional area of that cube is 12 by 12, and this is in centimeters squared. And of course here our answer for our H1 is going to be you realize that all those things cancel out. You remember, even these units, kilograms per meters cubed, cancel out with kilograms per meters cubed. So you remain that your height is going to be in centimeters. Now, of course, we were multiplying this kilograms per meters cubed by centimeter. Somebody would argue that would have to first convert this to meters cubed. It would still work out. If you were to convert this to meters cubed, it would mean that your answer here would still be in meters. But here we've done it in such a way that the kilograms per meters cubed are cancelling out, and we remain with figures that, and the units here are, we are getting our answer in centimeters. So the answer we are getting here is 6.88 centimeters. Now that 6.88 centimeters, this height we are getting is actually the height that of this solid that sunk in the surface of the mercury. But the question is not requiring us to find this height. If you go back to the question actually wants us to find what is the height of the block above the mercury level. So this is the height of the block that has been embedded into the mercury level according to our diagram here. So to get this remaining height, we know that this entire height is actually 12 centimeters. So to get the height of the block above the mercury level, the real height that they want is going to be equal to 12 centimeters. Subtract that 6.88. And when we subtract that, our answer here is going to become 5.12 centimeters. So 5.12 centimeters is actually the height of this mercury block that is above the mercury level. This question says that an object floats in seawater of density 1.03 times 10 to the power 3 kilograms per meter cubed, and it displaces 200 meters cubed of seawater. Find the mass of the object. Again, we are going to use the law of flotation, which simply states that the weight of the displaced seawater is the same as the weight of the object. So the weight of the displaced seawater is the same, or it's equivalent to the weight of the object that is actually floating. So now, of course, the weight of the displaced seawater is given by the mass of that displaced seawater. Multiply that by gravity. That is going to be equal to the weight of the object, which is given by the mass of the object. Multiply that by gravity. Of course, from here you see that the gravity and the gravity will cancel out. We have the mass of the water. Of course, mass of water is given by density of water. Multiply that by the volume of that displaced water is going to be equal to the mass of the object. The question wants us to find the mass of the object. So this is what we want, the mass of the object. So for us to get the mass of the object, we get the density of the water, which is 1.03 times 10 to the power 3. Multiply that by the volume of the water that has been displaced. Now the question says that it displaces 200 meters cubed of seawater. So it is 200 meters cubed that was displaced. That is equal to the mass of the seawater. And from this calculation, you find that our answer will be the mass of the seawater will be 206,000 kilograms. Glass block of mass 500 grams and density 2.5 grams per centimeters cubed floats in a liquid with 18.5% of its volume submerged in the liquid. Calculate the density of the liquid. Again, we are going to use this principle of flotation to interpret this. We are looking at a glass block, and this glass block is submerged in a liquid. So what does that mean? It means that the weight of the block is equivalent to the weight of the liquid it displaces. So the weight of the glass block is given by the mass of the glass block, let me call it mass of B, multiply that by the gravity is given by the weight of the liquid displaced, which is given by the mass of the liquid displaced, multiply that by the gravity. So we go ahead and find, of course, the g's are going to disappear. Then you find that the mass of the block, or the mass of the glass block, is 500 grams according to our question. So it's going to be 500 grams is going to be equal to the mass of the liquid. Now remember that we were interested in finding the density of the liquid. So the mass of the liquid is given by the density of the liquid, multiply that by the volume of the liquid. So to continue with our calculation, this is 500. 500 grams is going to be given by, now the density of the liquid here is what we are looking for. Multiply that by the volume of the liquid. Now here we are looking at the volume of the liquid that has been displaced. Of course, the volume of the liquid that has been displaced has not been given to us directly in the question, but we know that the volume of the liquid that has been displaced is equivalent to the volume of the portion of the solid that was actually submerged. So we just need to look for the volume of the solid that was submerged. And according to this here, we are being told in the question that 18.5% of its volume was submerged in the liquid. So 18.5% of the volume of this glass block was what was submerged. So it means that the volume of this liquid that was displaced is equivalent to 18.5% of, this is equivalent to 18.5% of the volume of the solid that actually got submerged, which is in this case, let me call it volume of the solid. So it is 18.5% of the volume of the solid. So now what is the volume of the solid? We know that the formula for volume of the solid can be gotten from, still our question, if we know that density is equal to mass over volume, so it means that volume is going to be given by mass over density. We have the mass of the glass block being 500 grams, and we do have the density of the glass block, which is 2.5 grams per centimeters cubed. So it means to get the volume is going to be, we shall say 500 grams is going to be equal to the density of the liquid, multiply that by 18.5%. Of course, 18.5, this is 0.185. Multiply that by the volume of the solid. The volume of the solid is given by the mass of the solid, which is 500 grams. Divide that by the density of the solid, which is 2.5 grams per cc. 2.5 grams. So of course, when we make this the subject of the formula, we shall end up with our answer being 13.51 grams per centimeters cubed. And this is the density of the liquid. A cross-sectional area of a ferry and its waterline is 720, that is at its waterline. A cross-sectional area of a ferry at its waterline is 720 meters squared if 16 cars of average mass 11,000 kilograms each are placed on board. To what extra depth will the boat sink in water? Again, this is a ferry and it is floating on top of water. And the principle is simple, that the weight of the water displaced is equivalent to the weight of the entire ferry. Let me try to draw this diagram. This is the ferry right there. And this is the water line we are talking about. Now the question is telling us that the cross-section area of the ferry at its water line, so while it is there, this is the water line, so the cross-sectional area there is 720 meters squared. So now if 16 cars of average mass 11,000 kilograms, so it means that you're going to put 16 cars and each car is 11,000 kilograms. To what extra depth will the boat sink? Of course, if this boat is to sink any extra depth, it means it's going to displace some water. And if it is to displace that water, the weight of that water that is displaced is going to be equivalent to the weight of these 16 cars that were put on the ferry. Why? Because it is these 16 cars that are responsible for this boat to sink that extra depth. So our work here is simply to find we simply need to just identify the fact that these 16 cars are the ones that are going to be responsible for this ferry to sink down an extra height or an extra depth, and so therefore the weight of these 16 cars that was put on this ferry is going to be equal to the weight of the fluid that will have been displaced at sea. So we begin with our calculation at that point. That weight of the water displaced is equal to, and of course, what is responsible for the weight of this ferry? It is these 16 cars that were added. So let's go ahead and find the weight of the water displaced. Of course, the weight of the water displaced is given by the mass of the water, multiply that by gravity. That is given by the weight of the ferry, which is comprised of the mass of the ferry, multiply that by gravity. Of course, these values of G will cancel, we remain with mass of water. The mass of water is given definitely by the density of that water in the sea, multiply that by the volume of the water. That is given by the mass of the ferry. Now for the mass of the ferry, according to our question, they are putting there 16 cars, and the average mass of these cars is 11,000 kilograms. So it means this is going to become 11,000 kilograms. That is the mass of each car, multiply that by 16 cars. That is the mass of the ferry. That's the cars they add, and they are responsible for the water we are trying to find. So the density, this becomes density of the water, multiply that by the volume of the water that has been displaced. The volume of the water that has been displaced is going to be given by the cross-sectional area of the ferry, multiply that by the height that sinks in, the depth that is sinking in as a result of these 16 cars that have been added on the ferry. So that is going to be equal to 11,000 times 16. So we're interested in this height because the question is asking that what extra depth will the boat sink in water? So the boat is already in water, but there's an extra depth it's going to sink, and that extra depth it is sinking, which we are calling H, is as a result of these 16 cars that they've added. So we make H the subject of the formula here and find that extra depth. So that extra depth H is going to be equal to 11,000, multiply that by 16, divide that by the density of water, multiply that by the A. Of course, this is 11,000 times 16 cars, divide that by the density of water, which we all know to be 1,000, multiply that by the cross-sectional area of the ferry, which is 720, and we shall end up with our answer being 0.024 meters. So the ferry sinks an extra 0.024 meters as a result of those added cars. A solid weighs 237.5 grams in air and 12.5 grams when total immersed in a fluid of density 900 kilograms per meter cubed. Calculate the density of the liquid in which the solid would float if a fifth of its volume is exposed above the liquid surface. If I may summarize this question, we are talking about a solid here. This is here. The question gives us some of it, the information of its mass. This solid weighs 237.5 grams in air. So this is its mass in air. So its mass in air is 237.5 grams. And then its mass when it is totally immersed in a fluid is 12.5 grams. And they're telling us that The density of this fluid is 900 kilograms per meter cubed. So calculate the density, the density of the liquid. So this is when this happens, as in it was going to, the mass of the fluid will be, the mass of this solid when it is in a fluid will be 12.5 grams when it is immersed in a fluid of this density. And now the question is asking us that what is the density, or calculate the density of the liquid in which the solid would float. So let's say this is the liquid we are talking about. So they want us to find the density of the liquid in which this solid would float if it had a fifth of its volume exposed above the liquid. So if we are having a fifth of this exposed, what would be the density of this thing? Of course, if it's a fifth exposed, it means below here it is 4/5. So here, below here, it is 4/5. 4/5 of the body is submerged, and a fifth is what is exposed above the liquid surface. And definitely, of course, now we are supposed to find the density of that liquid. So of course, still we are going to use the law of flotation, that the weight of this solid is going to be equivalent to the fluid, the weight of the fluid that has been displaced. So we will begin off from that point and say that the weight of this solid is the same as weight of fluid displaced. Let me call it liquid, because this one we've referred to as subscript L, weight of the liquid displaced. So what's the weight of the solid? Of course, the weight of the solid is mass of the solid mass of solid times gravity is given by the weight of the fluid of the liquid displaced. So it's going to be the mass of the liquid, multiply that by gravity, and of course the gravities will cancel out, you remain with mass of the solid. Now of course we have the mass of the solid, which you are calling the mass of the solid when it is in air. It is 237.5 grams. So we already have the mass of the solid, but then the mass of the liquid, we need to break this down further. So mass of the solid is given by mass of the liquid. Now for mass of the liquid, mass is given by density of that liquid, multiply that by the volume of that liquid. And so this means that mass of the solid is going to be given by the density of the liquid. Remember, we are looking for the density of that liquid that they are asking. That's what the question requires. The question is asking us that calculate the density of the liquid in which the solid would float with a fifth of its volume exposed. So this is the density we are looking for of that liquid. The density of the liquid, multiply that by the volume. Of course, the volume of the liquid that was displaced here is 4/5 of the volume of the body that was submerged. So it means that if you get 4/5, 4/5 of the volume of this solid that was submerged is equivalent to the volume of the liquid that was displaced. So it means it's going to become, multiply that by 4/5 of the volume of the solid. So now the thing is that we need to find the volume of this solid. We do not know the volume of the solid because we have the mass of the solid. We do not have the volume of the solid, but we knew the question requires us to find the density of that liquid. So our agenda now, we need to find the volume of the solid so that we come back and put it there. Maybe we can call this our first expression. So now we need to go ahead and find the volume of the solid. But how do we find the volume of the solid? We need to find the volume of the solid. We need to look at the information that has been given. From the information that has been given in the question, they've given us this, that when this solid is submerged in a fluid of density 900 kilograms per meters cubed, its mass is going to be 12.5 grams when it is submerged, and when of course the solid is in air, this is its mass. So given this information, this can help us to find the volume of the solid. If you look at this information, we can use Archimedes' principle. Remember, we were able to obtain this expression, using the law of flotation. Now let's use Archimedes' principle using this information that we are given to see where it lands us. Now, From Archimedes' principle, we know that upthrust is equal to weight of fluid displaced. From our question, upthrust, we've been given the mass of this solid when it was in air, the mass of this solid when it was immersed in the fluid whose density was 900 kilograms per meters cubed. Now the upthrust, of course, it is mass in air minus mass when the solid was immersed in the fluid. So in simple terms here, upthrust is going to be the mass of that solid when it's in air minus its mass when it's in the fluid. In other words, this upthrust, this apparent loss in mass, is equivalent to the upthrust. So mass in air minus mass of the fluid is going to be equal to the weight of the fluid displaced. Of course, this is mass in air minus mass in fluid. We shall multiply that by gravity, because here upthrust is equal to weight of fluid displaced. So, but the figures we have here are in grams. This is mass. So to convert them to weight is this mass times gravity. This mass, converting that to weight, is mass times gravity. So it's the same as saying the mass in air minus mass of when it is immersed in the fluid times gravity. This is the upthrust. Is going to be equivalent to the weight of the fluid displaced. Now the weight of the fluid displaced still is going to be given by the mass of the fluid, multiply that by gravity. Now of course the G and the G will go, they will cancel out, and so we shall remain with mass in air, which is 237.5 minus mass of the solid in fluid, which is given by 12.5 grams, is given by the mass of the fluid that was displaced. Now the mass of the fluid that was displaced here is still given by the density of that fluid, multiply that by the volume of that fluid. Of course, now this is going to give us 225 grams is equivalent to the density of the fluid. Now, according to our question, the density of the fluid is 900 kilograms per meters cubed. So this is going to be 900 kilograms per meter cubed. Multiply that by the volume of the fluid that was displaced. Now you realize this is in grams, this is in kilograms per meters cubed. It's only safe to convert this to kilograms as well to harmonize the units. So to convert this to kilograms, we shall divide by 1,000, so that this is also turned into kilograms. So now we make VF the subject of the formula. You find that the volume of the fluid shall be given by, in this case, it is 2.5. Multiply that by 10 to the power negative 4. That is meters cubed. So what does that mean? It means that we have found the volume when this solid was immersed in the fluid whose density was 900 kilograms per meters cubed. We find that the volume of the fluid that was displaced was equivalent to 2.5 times 10 to the power negative 4 meters cubed. But remember, when we talk of this being the fluid that was displaced, this fluid we are talking about of 900 kilograms per meters cubed, the question tells us that a solid weighs 237.5 grams in air and 12.5 grams when totally immersed in a fluid. So by the time it was immersed in this fluid of 900 kilograms per meters cubed, the question says it had been totally immersed. So it means if it had been totally immersed, and our calculations here is saying we have discovered that this is the volume of the liquid that had been displaced. It only means that the volume of the liquid that has been of the fluid that had been displaced is equivalent to the volume of the solid. So this means that the volume, this 2.5 times 10 to the power negative 4 meters cubed, is the same as the volume of the solid. So we shall simply write a statement and say that volume of fluid displaced in this case. So now that we've got our volume, the volume of the solid, so now we go back to our original expression. It means that we are going to get the volume of this and place it right there where we had stopped last time. So for us, we're interested in finding the density of the liquid. So it means to get back to this expression, we shall say, if I may rewrite it, the mass of the solid is giving us the density of the liquid. This is going to be equal to, so the mass of the solid in this case here is 237.5 grams, but convert that to kilograms by dividing by 1000. Is going to be equal to the density of the liquid, multiply that by 4/5 times the volume of the solid, which is this 2.5 times 10 to the power -4. So the density of the liquid in this case is going to become 1187.5 kilograms per meters cubed. In this session, we shall do a few numbers that require us to use Archimedes' principle and the law of flotation. Coming up. A piece of metal weighed 90 newtons in air and 80 newtons when completely immersed in water, whose density was 1 gram per centimeters cubed. Calculate the density of the metal. A piece of metal, its weight in air is given by 90 newtons, and when it's completely immersed in water, so its weight in water is 80 newtons. So that what's the density of the metal? Of course, now density of the metal, the formula is going to first find the relative density. After finding the relative density of this metal, then we shall go ahead and multiply that relative density by 1000, and we will be able to get the density of the metal. So we get started with the working. So relative density of metal, we shall quote the formula for relative density of metal. It's given by the weight of the metal in air, divide that by the apparent loss in weight. The apparent loss in weight of the metal when it was dipped in water. So the weight of the thing in air is 90 newtons. Divide that by the apparent loss in weight. Of course, the apparent loss in weight here is its weight in air. This is weight in air minus its weight in water. So in this case, it's going to become 90 minus 80. This is all in newtons. And we are going to end up with 90 over 10. That is going to give us 9. That's the relative density of the metal. So after getting our relative density of the metal, we will go ahead and now find the density of the metal itself. Of course, we get it from this expression. We know that a relative density of the metal can still be given by the density of the metal divide that by the density of water. And in this case, it's going to become the relative density of the metal here is 9. 9 is given by the density of the metal divided by the density of water. Now, according to our question, the density of water is in grams per centimeters cubed, so we shall maintain that it's going to be 1 gram per centimeters cubed. It means that the density of the metal we have there is going to be 9 grams per centimeters cubed, and that's our answer. So we move on to part B. Part B says that calculate the upthrust on the metal and the apparent weight of the metal when completely immersed in brine of that density. So now, of course, the upthrust on the metal means that this metal was dipped in water. When it was dipped, it experienced an upthrust, and that upthrust, according to Archimedes, is equivalent to the weight of the fluid that was displaced. So we're going to use Archimedes' principle to calculate part B. Now, in this case, they are telling us to calculate the upthrust on the metal and the apparent weight of the metal when completely immersed in brine. So we are dealing with brine here, yeah? So it means that, first of all, we first need to find the upthrust. And the upthrust we're dealing with is when it is in this fluid called brine, in this, as far as the question is concerned. So we go ahead and find the weight. So first of all, the upthrust. So the upthrust is going to be given by the weight of the fluid displaced. The weight of the fluid displaced is given by the mass of the fluid. In this case, the fluid is brine. So I'm going to say MB, mass of brine. Multiply that by the acceleration due to gravity. So what is the mass of brine? Of course, the mass of brine is not directly given in the question, but we know that mass is equivalent to density times volume. So it's going to become the density of brine, multiply that by the volume of brine, then multiply that by gravity, like that. So of course, from there we know the density of brine is given in the question as 1.2 grams per centimeters cubed. Now the volume of brine is not given in the question, but we know that this brine, the metal we are talking about was dipped in brine, and the question says that it was completely immersed. So if it being completely immersed, it means that the total volume of the metal is what was completely immersed in brine, and so the total volume of the metal is equivalent to the total volume of the brine that was displaced. We are to look at the brine that was displaced, the volume that was displaced. The volume of the brine that was displaced is equivalent to the volume of the metal that displaced the brine in the first place. So this is simple. We simply need to find to replace the volume of the brine. Since we do not have the volume of the brine directly, we simply substitute this by the volume of the metal that displaced the brine, and that one we can get it. We have the information, so we can go ahead and say this is going to give us the density of the brine, multiply that by the volume of the brine. The volume of the brine, you know that volume is given by mass over density. We know density is equal to mass over volume, so meaning that making V the subject to the formula, volume is going to be equal to mass over density. So in this case, since we're looking at the volume of the brine, it's the same as the mass of that metal, the metal that displaced it. So it's going to be given by the mass of the metal, divide that by the density of the metal. So the mass of the metal divided by the density of the metal gives us the volume of the metal, and the volume of the metal is the same as the volume of the brine, because it's the metal that actually displaced this brine we're looking for. So that is multiply that by gravity. So we shall go ahead here and fill in the figures now. This is going to give us the density of the brine, giving us being 1.2 grams per cc. Multiply that by the mass of the metal. In this case here, it is 90 newtons. Divide that by the density of the density of the metal. Now the density of the metal, of course, we got that in part A of the question. In part A of the question, we got the density of the metal as 9 grams per cc. So this is going to become 9 grams per cc. Multiply that by gravity, and our acceleration due to gravity here is 9.81. And so, of course, this grams per cc will disappear with those grams per cc. We have by 9 once, by 9 here it's 10. And we shall end up with our answer as 12 newtons. So we have answered that first part of the question, the upthrust. The upthrust is 12 newtons. That's the upthrust experienced on the metal. And now they're asking us to calculate the apparent weight of the metal when it is completely immersed in brine. So the apparent weight is given by, we know that when we are having this kind of metal here, that's the metal, it's in brine, right? We have its weight when it is in air, its weight in air, it's acting upwards, and then we have the upthrust force acting upwards like that. This is acting downwards, this is acting upwards, the upthrust force. So the apparent weight of the weight in air minus its weight when it is in brine, when it's in the fluid, gives us the upthrust force. And now, according to the question here, the question asks us to find the apparent weight of the metal when it's completely immersed in brine. So, of course, that the apparent weight is this one. The apparent weight is the weight when it is immersed in brine. That's its apparent weight. So we go ahead and find WB. Make WB the subject of the formula. Its apparent weight, or its weight when it is in brine, is given by the upthrust force, weight in air, minus upthrust. So this is going to give us its weight in air. Its weight in air is given in the question as 90 newtons. So it's going to be 90 newtons. Subtract the upthrust force. We got the upthrust force in the first part of the question as 12 newtons. And so in this case, our answer is going to become 78 newtons. A piece of glass has a mass of 52 grams when it is in air, 32 when completely immersed in water, and 18 grams when completely immersed in an acid. Calculate the density of the glass. So to summarize this question, a piece of glass has a mass of 52 grams in air. So its mass in air is given by 52 grams. Then its mass in water is given by 32 grams. And when it's completely immersed in an acid, this is mass in air, mass in water, then its mass in acid is 18 grams. Calculate the density of the glass. So of course, for us to be able to calculate the density of the glass, we are going to first find the relative density of the glass. After finding the relative density of the glass, then we multiply that relative density by the density of water, and we will be able to find the density of the glass. So we get started. How do we find the relative density of the glass? Of course, we shall get relative density of the glass is given by the mass of the glass when it is in air, divide that by the apparent loss in mass of the glass, so which is given by the mass of the glass when it is in air minus the mass when it is in water. So this is going to become the mass of the glass when it is in air is given by 52 grams. Divide that by the apparent loss, which is going to end up being 52 grams minus the mass when the thing is in water, which is 32. And so this is going to end up being 52. Divide that by 52, divide that by 20 gives us 2.6. So 2.6 is the relative density of that metal glass. So since now we have the relative density, we go ahead and multiply this by the density of water, and we will be able to get the density of glass. Of course, for us to be able to multiply this by the density of water, it comes from here. We know that still a relative density of glass is given by a density of the glass divided by that by density of water. So this is going to be given by the relative density of glass still is 2.6. We got it here, so it's going to become 2.6 is going to be given by the density of glass, divide that by the density of water. Now since the density of water in this case, according to our question, the density of water can be the density of water can either be 1 gram per centimeters cubed, or it is given by 1,000 kilograms per meters cubed. We can use any of them. The question does not specify, but since most of our figures here are in grams, then let's take this as our the density of water. Let's take it in terms of grams per cc, and of course here it's going to divide that by 1 gram per centimeters cubed, and of course definitely our density there, the density is of the glass is going to be given by 2.6 grams per centimeter cubed, or grams per cc. Of course, if you had used 1,000 kilograms per meters cubed, it means that your answer here would be in kilograms per meter cubed. That's the density of the glass. So what about the density of the acid? For us to find the density of the acid, we are going to pretty much use the same approach. We are going to first find the relative density of the acid, and after finding the relative density of the acid, then we'll go ahead and get that relative density and multiply it by the density of water like we've done in this, and we'll be able to get the density of the acid. So we'll begin by finding the relative density of the acid. So the relative density of the acid is given by the apparent loss in weight of that of this piece of glass. Remember, this piece of glass was first of all completely immersed in water first. Then after it's completely immersed in water, then it's also completely immersed in the acid. Now, of course, both when it was put in water and when it was put in acid, this piece of glass experienced some upthrust force acting on it. And now, for us to find the relative density of acid, it is the ratio of the upthrust force that was experienced when this piece of glass was put in the acid to the upthrust force that was experienced by the piece of glass when it was put in water. In other words, it's like saying it's the apparent loss in weight when the glass was put in acid, divide that by the apparent loss in weight when the glass was put in water. So that is the formula that we quote. So meaning the relative density of the acid is the upthrust experienced by the glass when it was in the acid. Divide that by the upthrust experienced when the thing was in water. This is the same as saying the upthrust experienced in the acid is the apparent loss in weight when it was put in the acid, which is given by the weight. In this case we have mass, so we shall use mass. So it's going to become the mass of when it is in air minus the mass of the piece of glass when it was in the acid. Divide that by the mass when it was in air minus the mass when it was in water. So the mass when it was in air from our question is given by 52 grams. So it's going to become 52 grams minus the mass when it was in the acid. The mass when it was in the acid is 18. So it's 52 over divide minus 18. Divide that by the mass when it was in air, which is still 52, minus the mass when it was in water, which is 32 grams. So this is 32 grams. We shall end up with 52 minus that is around 34. Divide that by 20. And we shall end up with 1.7 as our relative density of the acid. Now that we have the 1.7 as the relative density of the acid, we go ahead and find the density of the acid. So we shall get it this way. We know that relative density is still given by the density of the acid, divide that by the density of water. In this case, our relative density of the acid is given as 1.7. That's going to give us the density of the acid we are looking for. Divide by that by the density of water. In this case, we shall use 1 gram per cc. So it means our density of acid is given by 1.7 grams per centimeters cubed. That's the density of the acid. Okay, a balloon of negligible weight and of capacity 100 meters cubed is filled with helium of density 0.18 kilograms per meters cubed, and then part B, hydrogen of density 0.09 kilograms per meters cubed. The density of air is 1.2 kilograms per meters cubed. Calculate the lifting powers of the two balloons. Now, what do we mean by lifting powers? Of course, we said that when you drop, for example, when you are dropping in, when you dive in a pool of water, though for those of you who know how to swim, you always experience a force that is acting on you in the opposite direction. In other words, if you're jumping from a very high place up and you're going to fall in water, the speed with which you fall in air is not the same speed with which you fall when you fall into that water. In other words, immediately you fall in water, your speed reduces. It reduces because there is a certain force that is counteracting you. There is a force acting in the opposite direction, the upthrust force. And now this upthrust force exists in all fluids, and by fluids I mean both liquids and gases. So when you look at this here, we're looking at a balloon, and of course this balloon is not in a liquid. This balloon is floating in air, and it means that since air is a fluid, even it means that even the upthrust force is still going to work even in air. That's why balloons are able to float in air. They are able to advance up high in air because there is a certain upthrust force that is acting on it. Now, this lifting power that they are talking about is actually the upthrust force that is acting on these balloons. And we are being required now to calculate the lifting powers on the two balloons. So we shall first calculate the lifting powers on the balloon when it is filled with helium, then when it is filled with hydrogen. So let's begin with part A. I like summarizing my questions using diagrams. So let's assume this is the balloon we are talking about. Yeah? This is the balloon we are talking about. It is experiencing an upthrust force acting on it right there. So we are going to first find that upthrust force. Now, of course, in this balloon, if it is having some gas here, this gas has mass, and this mass is also acting downwards. So we are looking at, let's say, the mass of the gas, then we are looking at the force acting upwards, the upthrust, like that. So of course these two forces are going to cancel out. We are going to have the upthrust force which is equivalent to the weight of the gas that has been displaced acting upwards. Then we're having the mass of the gas inside this balloon acting downwards. So we find the resultant, we subtract them. Of course, this thing is lifting up. If it is moving up, it means that the upthrust force is stronger than the mass of the balloon that is trying to pull it down. So it means that we shall be getting this upthrust force, subtract that from the mass of the gas that is in here, and the difference in those two forces is going to give us the lifting power of this balloon. That is how we are going to approach this. So to summarize the question first before we continue, we have the balloon of negligible weight, so its weight is negligible. It has a capacity of 100 meters cubed. It means that the volume of the balloon is 100 meters cubed, and it is filled with helium. The density of helium is given by 0.18 kilogram per meters cubed, and then hydrogen, the density of hydrogen is given by 0.09 kilograms per meters cubed. Then we have the density of air. So we have the density of air also in play, which is 1.2 kilograms per meters cubed. So calculate the lifting powers of the two balloons. Let's first find this upthrust, the force that is trying to push these things up, the upthrust force. And from Archimedes' principle we know, and the upthrust force, according to Archimedes' principle, is equivalent to the weight of fluid displaced. Now, the weight of fluid displaced in this case is air. Air is the fluid that has been displaced. So we go ahead and find what's the weight of the fluid displaced. It's the air. So it's going to give us the mass of the air, multiply that by the gravity. What's the mass of the air? Mass of air is given by density of air, multiply that by the volume of air, then multiply that by the gravity. And of course, the density of air, according to our question, density of air is 1.2 kilograms per meters cubed. So this is going to become 1.2 kilograms per meters cubed. Multiply that by the volume of the air. Of course, the volume of the air that has been displaced is equivalent to the volume of the balloon, which is 100. So it's going to be 100. Multiply that by our gravity. Our gravity will be 9.81. And we shall get our answer as 1177.2. This is the lifting power. Now that we know the lifting power of this balloon, the force that is acting upwards. Oh, this is okay. It is the force acting upwards. It's not exactly the lifting power of the balloon. It is the force that is acting upwards. But now the lifting power is going to be a resolution of the force acting upwards minus the force acting downwards, and the force acting downwards is a result of the mass of the gas in that balloon. So now that we have gotten the force acting upwards, we shall go ahead and find the mass. For example, when we are dealing with helium has that density. So let's go ahead and find the weight of the helium. When helium is in here, what force is exerted downwards? So if helium was inside here, what would be the force it's exerting? In other words, what would be the weight? So we know that the weight of helium is going to be equal to the mass of helium, multiply that by gravity. Now the mass of helium is given by the density of helium, so density of helium, multiply that by the volume occupied by helium, multiply that by gravity. In this case, the density of helium, according to our question, is 0.18, so it's going to be 0.18. Multiply that by the volume of helium. Of course, the volume is the same as the volume of the this balloon, which is 100 meters cubed. So this is times 100. Multiply that by the gravity, which is 9.81, and when you sum that up, you end up with so we shall end up with 176.58 newtons. That is the weight, that is the force of the helium gas when it is inside here. So now let's look. So now what is the true lifting power when helium is in this balloon. So we are going to get the upward force minus this downward force, and we shall get the lifting power when it is helium in the balloon. This is going to give us upward force minus the downward force. So what did we get as our upward force? Upward force is this. Okay, I had called it lifting power earlier, but I think the accurate word is to look at it as our upward force. So our upward force is going to be equal to 1177.2. So it's going to become 1177.2. Subtract the downward force, which is the weight of the helium, and in this case it is 176.58 newtons. So our answer there, after subtracting it, now this is now the lifting power when we are having helium in the balloon. So we're going to use the same approach, and we are going to find the lifting power when we are having another gas in the balloon. So the same procedure will apply when we are having hydrogen in the balloon. So we'll go ahead and find the weight of this balloon when there is hydrogen in here. Of course, so weight when it is hydrogen in the balloon is going to be given by the mass of hydrogen, multiply that by the gravity. This is going to be given by density of hydrogen, multiply that by volume of hydrogen, multiply that again by gravity. So the density of the hydrogen is given by that 0.09. That is in our question. Multiply that by the volume of the hydrogen. Of course, the volume multiplied by the hydrogen is equivalent to the volume of the gas, which is 100 meters cubed. Multiply that by gravity, which is 9.81. And what do we end up with? 88.29 newtons. That is the weight of this gas when it is in the balloon. So now the lifting force, again, we are going to find the upward force minus the downward force. The upward force, we obtained it earlier again as 1177.2 newtons. Subtract the downward force in this case, which is 88.29 newtons, and definitely the lifting force when hydrogen is in the balloon is 1088 newtons. A hydrometer of mass 30 grams floats in water of density 1 gram per cc with 4 centimeters of its stem out of the water. The cross-sectional area of the stem is that 0.5 centimeters cubed. The question requires us to calculate the total volume of the hydrometer and the length of its stem out of brine when the hydrometer floats in brine of this density. So we'll begin with part A, but before that, we summarize the question as usual. We have a hydrometer, its mass is 30 grams. So we have the mass of the hydrometer giving us 30 grams. This thing here, it's floating in water, and the density of that water, they're telling us the density of the water is 1 gram per cc with that is with 4 centimeters of its stem out of the water. Of course, now when we are dealing with I'll draw the sketch still. We're having, that's like the hydrometer, and 4 centimeters of its stem is out of this water right there. The cross-sectional area of the stem is 0.5, so meaning that the area of the stem, the cross-sectional area of the stem is 0.5 centimeters squared. Now that we've summarized our question, we're being told to find the total volume of the hydrometer. Now we all know that when we're dealing with a hydrometer such as this, it operates on the principle of buoyancy, or the principle of flotation. The law of flotation, it states that for every floating body, a floating body will only displace its own weight of fluid. And so this hydrometer works on that principle, that when you drop it in water, it's going to float. And when it floats, its weight, the weight of this hydrometer, is equivalent to the weight of the fluid it has displaced. And so meaning that if we want to find the total volume of the hydrometer, then we are going to figure that out from the principle with which it works. It works on the principle of flotation, and that is where we are going to begin from to find the volume of this thing. So we'll begin by saying the weight of this hydrometer when it's in water, when it floats in water, its weight, or the weight of hydrometer, is equal to the weight of the water it's going to be displacing. That's the principle of flotation. So what's the weight of the hydrometer? The weight of the hydrometer is given by the mass of the hydrometer, multiply that by the gravity, or it's going to be given by the weight of the water displaced, which is given by the mass of the water, multiply that by gravity. So of course the g's will cancel out, the gravities will cancel out, and we remain with mass of hydrometer here. Of course, mass of hydrometer, we already have it here as 30 grams, so we can maintain that mH. So mass of hydrometer is going to give us the mass of the water. Mass of water is given by the density of the water, multiply that by the volume of the water. And so this is going to give us the mass of the hydrometer is given by the density of the water. We already have the density of the water. Multiply that by the volume of the water. Now, from the volume of the water that has been displaced, this is our sketch right here. This is the hydrometer, it has sunk in. Now, of course, the volume of the water displaced is going to account for a certain portion of the hydrometer stem. Now, we already have the cross-sectional area of the stem, which is 0.5 centimeters cubed. So it means that if we want to find the volume of the water that has been displaced, it's simply going to be equal to the cross-sectional area of the stem here, the cross-sectional area times the height that has sunk in the water, the height that has been submerged. The height of the stem that has been submerged, multiply that by the cross-sectional area of the hydrometer, is what is going to give us the volume of the hydrometer. But the thing here is that we do not know the height that has been submerged. The question is only giving us the height that is exposed. If you look at the question, it's saying that 4 centimeters of each stem is out of the water. So it is 4 centimeters that is out. For us, we're interested in the height that has been submerged, because it is this height that is going to give us the volume of the water that has been submerged. So we can simply, we can call this whole height, the entire height of the whole hydrometer, let's call it x. And so it means that the height that has been submerged here is going to be x minus 4. So it means that the volume of the water that has been displaced is going to be given by, that is going to be multiplied that by the area, the cross-sectional area of the stem, times the height that was submerged, which is x minus 4. And you realize that this x so happens to represent the height of the entire hydrometer. If we're able to get this value of x, the height of the entire hydrometer, then we simply multiply that x by the cross-sectional area, and we will be able to answer the first part of the question, which is asking us to find the total volume of the hydrometer. So let's continue. This is going to become, so we find the value of x, in other words. So this is going to become mass of hydrometer. The mass of hydrometer is 30 grams. So it's going to become, mass of the hydrometer here is 30 grams, is giving us the density of water, which is 1 gram per cc, which is 1 gram per cc. Multiply that by the cross-sectional area. The cross-sectional area is 0.5. That's 0.5 cc. Multiply that by x minus 4 centimeters. And so definitely this is going to become 30. It's giving us, this is a half into x minus 4. 60 is giving us x minus 4. We end up with our value of x as 64 centimeters. So 64 centimeters, this is the value of x. It means that that is the height of this whole stem of the hydrometer. But now the question requires us to find the volume of the hydrometer. Since we have the total height of the entire stem, so we can go ahead and find the volume. Therefore, the volume of the hydrometer is given by the cross-sectional area of the stem, multiply that by its height, which height so happens to be x. So the cross-sectional area is going to 0.5 centimeters cubed, multiply that by the height, which is 64 centimeters, and our answer, therefore, it's going to end up being 32 centimeters cubed. or this area, or cross-sectional area, is centimeters squared. So it's 32. That answers part A of the question. So part B of the question is asking that to find the length of its stem out of the brine when the hydrometer floats in brine of density 1.2 grams per cc. So now we have gotten this. It is now floating in something else. It has now been put in what we call brine. And now the question asks us to find the length of its stem out of the brine. They want us to find that length out of this brine when it is with this. So the principle we use is the principle of flotation. The law of flotation, that this hydrometer, when it was dipped into this brine, it is going to only displace its own weight of fluid. So it means that the weight of this brine, the weight of this hydrometer, is equivalent to the weight of the brine that has been displaced. So we begin from that point. So what is the weight of the hydrometer? The weight of the hydrometer is given by the mass of the hydrometer. Multiply that by gravity is giving us the weight of the brine displaced, which is going to give us the mass of the brine. Multiply that by the gravity. The g's cancel out. So when the g's cancel out, we have the mass of H is equal to m of B. The mass of the hydrometer, of course the mass of the hydrometer, the question tells us it's 30. So we already have the mass of the hydrometer. So it's going to be 30, is going to be given by the mass of the brine. The mass of the brine is given by the density of the brine, multiply that by the volume occupied by the brine. So this is going to become 30, is going to giving us the density of the brine. According to our question, the density is 1.2 grams per cc. So it's 1.2 grams per cc, multiply that by the volume of the brine. Multiply that by the volume of the brine. Now this is going to become, this is 30, is giving us 1.2, multiply that by the volume of the brine. Now the volume of the brine, if you look at our sketch, the volume of the brine is equivalent to the volume that was occupied by the hydrometer. So it's going to be the cross-sectional area of this hydrometer times the height. So it's going to be equal to, the volume is given by the cross-sectional area of the stem, multiply that by the height that is occupied by the brine, which we do not know. Let's call that H. The height, the height that was submerged, the height of the hydrometer that was submerged, we've called it H. So we find the height that was submerged in this case. So this is going to become 30. It's going to be, this is 1.2, which is going to be the same as 12 over 10. Multiply that by the cross-sectional area of the stem. According to our question, the cross-sectional area is 0.5, which is the same as a half. Multiply that by H. So this is going to become by 2 ones by 2. This is 6 by 50. So we've got our value of H as 50. Our value of H as 50 means that when we dipped this hydrometer into the brine, the height here was 50. So now that we have the height that is getting in here, which is 50, the height submerged, the question requires us to find the length of the stem out of brine. So of course the length of the stem that is out, which is this one here, is going to be given by the length of this whole thing minus the length that is submerged. So let's call it y right here. So it means that to find the value of y, which is the length of the stem out of brine, will be given by the length of the whole stem. Now we got the length of the whole stem in our previous calculations as 64 centimeters. Right there, this 64, this is the value of x we got when we were doing part A. That's the length of the whole stem. So this is given by 64 centimeters, subtract that minus 50. And 64 minus 50 gives us 14 centimeters. That is the length of the stem out of brine. The length of a light spiral spring is 200 millimeters when not stretched. It means that that's its original length when it's not stretched. So the spring obeys Hooke's law. I assume that you all understand Hooke's law, that when you apply a force on a string, the force applied on an elastic string is directly proportional to the extension, provided the external limit is not exceeded. So the spring obeys Hooke's law. A solid of mass 1 kilogram is hung from the lower end of the spring and its length becomes 254 millimeters. When the solid is totally immersed in water, the length of the spring becomes 227 millimeters. Calculate the upthrust on the solid and also calculate the mass and the volume of the water displaced by the solid. So we'll begin with the first portion of the question, but this is a long question. We'll first summarize it diagrammatically. So we have the length of a light spiral spring. This is a light spiral spring. Its original length, let's say length of the its original length according to a question is 200 millimeters. So it is 200 millimeters. So the spring, that is when it's not stretched, meaning that's its original length. Yeah. So this it obeys Hooke's law. Okay. A solid of mass 1 kilogram is hung from the lower end of the spring. So we are having a mass of a mass of 1 kilogram. So a solid of mass 1 kilogram is hung from the lower end of the spring and its length becomes 254 millimeters. So meaning that when this mass is hung, its length, let's call it L1, becomes 254 millimeters. This is the length of the spring when it is not stretched. This is the length of the spring when it is stretched or by this mass of 1 kilograms. And since it obeys Hooke's law according to what the question is telling us, then it means that the extension experienced by this spring is going to be the final length minus the original. 254 minus 200 to give us 54 millimeters as the extension. Now, of course, the question goes ahead to tell us that when the solid is totally immersed in water, so here it was at first on its own, this is what it experienced when it was in air. Now when we go ahead and immerse that solid in a vessel of water, what happens to the spring? The question says that the length of the spring becomes 227 millimeters. So it means that, let's call this L2. So the length of the spring becomes 227 millimeters when this piece with this spring is stretched by that mass. When this mass is immersed in water, it's 227. So if it is 227 millimeters when it's in water, so meaning what's the extension here? Of course, the extension there is going to still be this minus the original length. In this case, the extension is 27 millimeters. We obtain that by getting the new length when it's in water, which is 227, minus the original length of the string when it is unstretched, which is 200 millimeters. So we've summarized it to that point. So now they're asking us to calculate the upthrust of the water on the solid. So when it's in the solid, what's the upthrust? Of course, we know that upthrust, we are going to use Archimedes principle to interpret this. And we know that Archimedes principle is that when a body is wholly or partially immersed in a fluid, it's going to experience an upthrust force. And that upthrust force is equivalent to the weight of the fluid displaced. So upthrust, in this case, is given by, of course, we have this metal, which, let's call it a solid substance that is weighing 1 kilograms. When it was weighing 1 kilograms, at first, these are the dimensions when it was in air, and this is what happens when it is in water. Since it obeys Hooke's law, it means that we can find the force or the weight of this substance in air, and then we can also get the weight of this substance when it is in the liquid. Because the upthrust force here is given by the weight of that substance when it is in air minus the weight of that substance when it is in water. So it means that we simply need to find its weight in air and its weight in water to get the substance, to get the upthrust. Now, of course, its weight in air, we can get it here first. Its weight in air is given by its mass in air multiplied that by gravity. Its mass times the gravity. The mass is 1 kilogram, multiply that by the gravity. Now the gravity for this question, we are going to use our gravity is going to be equal to 10 meters per second squared. So it means that our gravity is 10. So it means that the weight of that substance when it is in air is 10 newtons. We are using gravity this time around as 10. So we've gotten our weight in air. What about our weight in water? Now for us to get our weight in water, we are going to use Hooke's law. We are going to use Hooke's law to find its weight in water. So here I'm going to attempt to find the weight of this substance when it is in water. First of all, the weight when it is in air has been gotten here. Let me call that its force, or the weight when it is in air, is given by 10 newtons. We already established that as 10 newtons. So what is its weight when it is in water right here? So of course from here we know that Hooke's law is given by force is going to be equal to K, the spring constant times the extension. Now this is on the assumption that you have covered Hooke's law and you understand what I'm doing. I'm not going to go so much into the details of Hooke's law and how it all comes about. So F, in this case, the force or the weight of that is, we got it as 10. 10 is going to be giving us the spring constant, which is K, times the extension. The extension here is 54 millimeters. Now you realize that this 10 is in newtons and this 54 is in millimeters. So to harmonize these units, we divide this by 1,000 so that it becomes, to convert it to meters, so that our value of K is going to become 1,000, divide that by 54. So this is our spring constant K. Now that we've got our spring constant K from this information, we are going to use that same information to try and find the force or the weight of this when it is immersed in water. So to find that, we shall simply say that the force from Hooke's law, force is given by K times E, where K is the spring constant. The force in this case is the same as the weight exerted by this solid substance. So this is going to be given by what is the spring constant K. Since it's the same spring, it means that this constant K we got here when we are using this is the same here. So the value of K here, we said it's 1,000. Divide that by 54. Multiply that by the extension. The extension, when it was dipped in water, we got it as 27. So it is 27 millimeters. But now, since this is 27 millimeters and this is in, we convert it to meters to harmonize the units, because even the force we're supposed to be getting here is supposed to be newtons. So we divide that by 1,000. So this is 10,000. This is 10,000 times that, divide that by 1,000. So to get the force, the weight of this thing when it is in water is, the answer is, we end up with 270, divide that by 54, and our answer in this case is 5 newtons. So it means that when this thing was in water, it weighed 5 newtons. So we shall come back to our expression here and say, we already have weight in water, we got it as 5 newtons. We got the 5 newtons from here. So it means that our upthrust, in this case, upthrust force is going to be equal to weight in air, which is 10 newtons, minus weight in water, which is 5 newtons. So meaning our upthrust force in this case is 5 newtons. And that's our answer. We have answered the first part of the question that required us to calculate the upthrust of the water on the solid, which we got as 5 newtons. Now the other part is telling us that calculate the mass and the volume of the water displaced by the solid. Again here, we are going to use Archimedes principle. And now to calculate the mass and volume of the water displaced, we know that upthrust. Now we already got upthrust in our first portion of the question. Calculate the upthrust, the first portion. So we got our upthrust as 5 newtons. This is going to be equal to the weight of the fluid displaced. Of course, the weight of the fluid displaced here is given by mass of that fluid, multiply that by gravity. So we continue. This is going to become the mass of that fluid. In this case here, we are dealing with mass of water. So the mass here, this is what we want. According to calculate the mass first. So we make this subject to the formula. Of course, it's going to become the mass of the water, multiply that by gravity, which is 10, is giving us 5 newtons. Of course, the mass of the water in this case is going to be given by 5 over 10, which is 5 newtons, divided by that by 10, giving us 0.5 kilograms, which is the same as 500 grams. So the mass of the water is 500 grams. So we go ahead and calculate and volume of the water displaced by the solid. Now that we have the mass, we can go ahead and find the volume. The volume of the water displaced is given by the mass of the water. Divide that by the density of the water. So in our previous calculation, we got the mass of water as 500 grams, so this is going to become 500 grams. Divide that by the density of the water, which is 1 gram per cc, and it means that the volume of the water in this case is 500 centimeters cubed. So that answers the other portion of the question. Volume of the water displaced is 500 centimeters cubed. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.